My topic of discussion is high and actually higher viscosity water-based inks for Inkjet. And yesterday, during one of the break sessions, I had an interesting discussion with one of the participants. And I guess they have been following, the developments and the innovations from ZAR. And they asked me a question that, to make these high and higher viscosity inks, is it easy to do that? And the answer I gave was, it is actually challenging to do that. And my perspective is, it is those challenges that bring out, the opportunity to think differently and the opportunity to do innovation and to bring about originality. So my message today is to give you a perspective from a formulation point of view, to look at the formulations and to outline things which makes it challenging, and to show you some of the opportunities why the inks themselves have the potential to be disruptive in the market, to offer benefits in terms of helping Inkjet to bridge the gap with conventional printing. So just before we do that, a bit about Nazdar. Nazdar is a global ink manufacturer, as you may be aware, with a headquarters in Shawnee in the United States. But we have multiple R&D centers and multiple production centers, and we have a number of distribution centers across the globe. And Nazdar manufactures inks for inkjet, for screen printing, for flexographic printing, and across various chemistries, water, UV, LED, and so on. So that's a little bit about Nazdar. But what I am really excited to do is to speak to you about the high viscosity water-based ink series from Nazdar. And over the last year and a half, we have been developing these inks, and some of these inks are dedicated to the textile application, DTG, DTF for example. And we have another series which is dedicated to the corrugate marketing, and it allows barcodes to be produced, it allows images to be produced on cardboard. And I'm aware that some of you have been following the display by ZAR and some of the image qualities that they have been demonstrating and so on. So we have these series, and these were developed and optimized so that they can offer benefit and fitness for purpose in each of the sector. So these are ready, and they are ready for the market, and some of these are in beta testing in the field and so on. So please do come and speak to us about any of these if there's any interest. As I was saying, this is about high viscosity and actually going higher in viscosity. And I think it is important just to put it into context. What is typical for inkjet is low viscosity at the jetting temperature. The jetting temperature is critical. Typically, this is fluids, 4 centipoise, 8 centipoise, 10 centipoise, higher at the jetting temperature. Outside of the jetting temperature, ink viscosity can be higher. But at the jetting temperature, it's critical to understand that we're talking about viscosities less than 20 centipoise. But what we're talking about in this presentation is inks which we have developed, which are functional, with viscosities at the jetting temperature 60 to 70 centipoise. And I think that's significant. So what this does, I think it means that the window of opportunity for inkjet becomes wider, becomes larger. And with that comes the opportunity to make the fluids more functional, as I will outline in the course of the presentation. So what do we achieve? If we look at this, we can see that this is printed with ZAR's Aqueous head using Nazdar's high viscosity coding and marking black ink. But what we can see is at 15 degrees, this is 116 centipoise. And that's a huge viscosity. At 20 degrees, this is 85 centipoise. At the jetting temperature of 25 degrees C, this is 63 centipoise. But I think for me, it's the quality of the print, it's the definition which is achievable here for this coding and marking application. And look at the density, 1.24. That's a significant achievement, I thought. Let's look at some more examples. Again, Nazdar's high viscosity series for the corrugate application. It's about the blackness of the black print. And to be able to do that using a single pass, I think that's what makes it interesting. Flexible packaging, for example, it's the definition and it's the quality and it's the color density, I think, which is achievable using a single pass printing. On the right, we can see a coding and marking print. And there we can see the barcode, we can see the QR codes, and we can see the quality of that. And again, to be able to achieve that using single pass. Towards the bottom on the right, again, we can see a textile high viscosity fluid, a white ink which was developed specifically for that market sector, applied using a single pass printing to be able to achieve that density, which I thought is remarkable. So then, what is on offer? I think if you look at the fluid point of view, and as I said, if we consider that what high viscosity does is it widens this window of opportunity, it widens this window of viscosity. So what it allows us to do is to be able to achieve higher density. Obviously, to do that is to be able to put more pigment in formulation, to be able to put more binder so that we can have better wetting, we can have controlled wetting, and so on. And in porous media, that offers the opportunity to be able to have inks which sit on the fabric and which sit on the corrugate boards, for example, if this is a corrugate application, and then you can have this stacking which gives you the density that is achievable. And I think it's about the opportunity of that bigger window to be able to have high functional components incorporated into the fluids. So I think, again, this is what high viscosity offers. And it offers the opportunity, obviously, if one wishes to use less carrier and to maximize how much pigment, how much binder can be used in formulation so that density, wetting can all be controlled and optimized. And in terms of, because the density is high, you have the opportunity, I think, as it was demonstrated yesterday, to go faster, single pass versus multi-pass, for example, compared to standard viscosity. And so I think that offers the opportunity to print faster, but the opportunity also to be able to dry faster if that is a requirement. As I said at the start of this discussion, these advantages come with challenges. And let me highlight some of those challenges. From a fluid point of view, when you open that bigger window and you put in more active ingredients, you put in more pigment, more binder, you need to consider fluid stability. It becomes a lot more challenging. The rate at which pigments settle, the rate at which interactions occur become even more prevalent. And flow and rheology. Obviously, you put in more binder, and then you face rheological difficulties. In certain instances, by putting more film former, then you need to consider how much that affects open time, for example, which is a critical factor in the printing process. Elasticity, for example, and how that dictates, the flow through the nozzles and, the jetting and the ejection of the droplets. So it becomes more challenging by opening this window, and in many instances these fluids are at the critical points of either viscoelasticity, for example, or film formation. So it requires a lot of thinking differently in order to mitigate and overcome these challenges. And if one is not careful, then print artifacts can arise in the formulations, obviously because of the use of higher components in the formulations. And that is the concept of going faster and making sure that one addresses and ensures that the quality of the prints are good enough for the printing process. So let me give you a few examples. What is important, which is the question here? How do we ensure that we have optimum performance in these high and higher viscosity formulations? And I think for me it's about striking the balance, ensuring that the formulations are considered and are tailored to ensure that, you know, the jetting performance is not compromised. If the jetting performance is compromised, then you can have print artifacts, then you can have problems with open time. But it's about balancing the formulations, about balancing the inks, and making sure that when you choose your components, when you choose your solvents and your binders and the levels of your pigments, you do not compromise stability, which is very, very important. If stability is compromised, then the performance, the rheology, the flow of the inks are affected. So it has to be good stability, excellent stability. And in terms of rheology, mitigating viscoelasticity, mitigating flow artifacts, then the rheology of the formulations will need to be good and excellent. And to be able to do that and balance the amount of carrier and humectants, and by selecting the binders, then that is one way that we can control open time, which becomes critical. And all of these then feed into, you know, the ink systems and how the print heads perform, and then we can have better jetting and better interaction between the inks and the substrates, and so on and so on. Let's look at this example, and this is to say that here we have two inks, and these two inks, they have the same viscosity, which is 63 centipoise at 25 degrees C. These two inks utilize the same pigment dispersion. They utilize the same amount of pigment. But as we can see, as we go from left to right, that this rate of settling of the pigment is different. And the only difference between these two white inks is a minor difference in composition. But why is it that a minor difference in composition affects fluid stability, affects the rate at which you know, the pigments settle? In fundamental terms, pigments are particles. When they are in a dispersed system, they are influenced by factors such as Brownian motion. And because we have the same amount of pigment, we have the same level of dispersions and dispersions, but then it's not only viscosity which becomes fundamentally important, and there are other factors in the formulations which we have to bear in mind. So the message here is that beyond viscosity, which we use as a lever to pull in order to give these benefits to these formulations, which give benefits in these printing applications, but we have to consider other factors outside of that. And here it's about interactions and about understanding these interactions which arise in these formulations between these components, and how we can control that and how we can mitigate that. And I will come back to interactions shortly. Let me give you another example. This is a high viscosity white ink, which is about 52 centipoise at 25 degrees C. Single pass, applied on a flexible film, and it's the definition and it's the density of the white which is achievable on a flexible film. But this is a highly dense ink with high levels of solids, because that's what we tend to focus on in achieving high viscosity. And the substrate is non-porous, and we print under higher humidity conditions in order to, you know, have good open time and so on. But then drying becomes challenging. Then again, it's about the fundamentals and understanding what becomes important. Is it that we should have higher airflow? Should we increase the drying temperature? Should we increase the drying time? Perhaps not, because they come with cost implications. Nobody wants to do that. But I think, again, going back to the fundamentals, it's about making sure that, you know, we use the fundamental science to understand what else can we do in these formulations. How can we choose our components? How can we choose our binders? How can we choose our carriers? By looking at the boiling points, the evaporation rate, the film formation temperature, and so on, so that we can have high density formulation, but we can also mitigate and achieve good curing and good drying in these inks. As I said, I will come back to interactions. From the fundamental point of view, we have pigments, we have binders, we have polymers, we have additives, and these additives could be wetting agents, could be deformers, could be whatever. It's important to understand what they do, and as we open up this window, and this bigger window of higher viscosity, if we consider pigments, and we consider that these tiny nanoparticles, and if we say, imagine that these are dancers on a floor, and it's about the rhythms which they move, and it's about what they do when they come together, and it's about understanding how we can control that, and we can ensure that that doesn't affect, say, that doesn't cause settling in the inks, but that we can mitigate that, but we can achieve the color intensity that we need in the formulations. And if we imagine polymers, obviously, with their dangling ends, with their, you know, branching, where there is branching, and if we imagine, you know, the way in which the molecular materials interact in the formulations, and the way in which physical and chemical forces in the formulations dictate how components interact, whether this interaction is between the polymers themselves or the polymers and the other components. But again, it's understanding what that means and controlling that and ensuring that is kept in harmony. If we imagine the polymers and the pigments, for example, and if we imagine how these are together in a matrix, but it's about ensuring that the dispersion is effective, it does the job, and I think that becomes important, that becomes even more important as we make these high and higher viscosity fluids. Let's consider the additives. Let's consider that these are architects, for example, and it is these architects which shape the mechanical properties, the films themselves, which help the wetting, which help remove foaming in these systems. These are water-based formulations, and they enhance and promote flow, for example. But we have to make sure that we control these, and we have to make sure that, again, additive polymer or additive pigment interactions are not detrimental in the formulations. And finally, we have to make sure that, you know, these additives, when they combine, they give you these additive effects, because that's what they are supposed to do. That they give you these synergistic effects so that you achieve, you know, functional fluids. You do not want any antagonistic effects, so that these components are working against one another, ruining the formulations and inducing sedimentation. So it's about the fundamentals of the formulations. And that's the message which I wanted to pass across, to say that as we make these high viscosity and higher viscosity fluids, it's the fundamentals of the formulations, of the science, which we need to make sure is right. And if it is right, then the fluids are functional. So to summarize, I think it's clear from, I think, what we saw yesterday from these discussions, that high viscosity inkjet has the advantage and opportunity to help inkjet bridge the gap with analog printing. And I think that is the opportunity. Obviously, by widening that window, we can increase the amount of functional materials that we put in the formulations. And obviously, I think there is the opportunity, obviously, to use less water if we need to, or use more water if we need to, use other components, achieve more sustainability in these fluids. And obviously, I think it offers the opportunity to have more energy efficient formulation so that we can have faster drying if we need to, and so on and so on. So I will stop here, but thank you for your listening.
Thank you.